Awesome. So pleasure to have with us today Dr. David Alvarez-Melis from Harvard University, where he's an assistant professor of computer science at the School of Engineering and Applied Science. He leads the data-centric machine learning group there and is also an associate faculty in the Kepner Institute. In addition, he has affiliations with the Center for Research on Computation in Society and the Harvard Data Science Initiative. He's also, in addition to his position at Harvard, a part-time researcher at Microsoft Research New England, and his work really focuses on how data shapes the reliability and behavior of AI systems. So it's a pleasure to have him with us today. David, welcome.
Thank you. Thanks for the introduction. Welcome, everybody. Thank you for the invitation. I'm very happy to be here. It's my first time at CMU and in Pittsburgh, so I'm glad to be here. So today I prepared a talk that tries to give a unified view of many of the threads that are happening in my group at the moment. And I think the best way to frame them is through this lens of turning discrete choices, many of the discrete choices that we have in machine learning, and sort of pushing them to a continuum limit that makes those choices easier to deal with and more tractable. And the motivation for this is, as you're probably aware, especially if you work in machine learning, is that the machine learning practice is full of these discrete choices. We have to choose, for example, model sizes, and typically you are offered just a limited number of model sizes. And by the way, here when I say discrete, I know that many will argue that most of the things we do in computational methods is discrete. At the end of the day, we rarely work with actually continuous objects. So for the purposes of this talk, when I say discrete, typically I mean a small set of coarsely grained objects. For example, model sizes, right? So you might want to download a model from Llama or Qwen, and then you find only kind of 3 very sparsely sampled model sizes. Maybe you're looking at different pre-trained models with different capabilities. And again, you have a limited finite set of choices. You need to decide the depth or width of your model. And again, that involves a coarse discrete choice of architecture. And also in terms of data sets. When you're about to train your model, you need to decide which data set you're going to pre-train it on. So all of these are different instantiations that I think share an underlying cause, which is computational constraints, right? It would be, of course, much easier if Meta would offer all possible sizes of models from 1 billion to 100 billion, but that's not sustainable. So there's some choices that go into deciding, okay, these are the thresholds, these are the models that we will offer or service for machine learning providers. And same with data. We have data constraints. There's provenance aspects that make these choices sort of given, and there's nothing we can do about the discrete nature of them, except, as we'll see in the rest of this talk, making better use of them. So just some limitations of this aspect of discrete choices. First of all, as I've been hinting at, it implies a fragmented design space. There's limited choices we can do, and then when we're trying to make those choices, especially if you have to make those 4 choices at the same time, you end up with this combinatorial explosion of possibilities that is hard to navigate and optimize over. We have these isolated points that we don't have anything in between. So maybe what we really want is something that is in between a model that was trained on a certain domain and another domain. We don't have that. So we have this binary choice of going with either kind of model. This kind of paradigm is not very adaptive in the sense that maybe the model that I would want is the one that exactly fits in my GPU, and that would be a 50 billion model parameter, but I don't have that option. So I have to either underutilize my GPU or I couldn't overutilize it. So I end up with a suboptimal choice of model. This also leads to discontinuous jumps that we see often in machine learning results. And there's also a lot of redundancy. If we have multiple models that maybe share some aspects, instead of having a modular version of them where you could store a shared set of parameters, you end up with duplicated copies stored across. So the fact that we have these individual discrete choices often implies that there's no information sharing across them that would make storing them and working with them much more efficient. So this is sort of the landscape. And what I'm proposing and advocating through this line of research is essentially smoothing out these choices into something that is more continuous or quasi-continuous. So what might this look like in a very sort of high-level conceptual way? So the first principle would be, if we have disconnected points, we might be able to draw paths between them and then choose everything that is in between those 2 points. We might be able to go from fixed categories to smooth spectra that interpolate between them. Instead of having one-off solutions that are unrelated in practice, we can try to relate them through shared aspects, shared geometry, shared characteristics, and then have a family of solutions that sort of share information of some kind. And also, we might be able to mitigate this issue that we often have, that we see these sharp transitions in behavior and performance, emergence of capabilities that look like emergence only when you have a discretely sampled set of choices. But if you have smooth interpolation, if you have more choices in between, you see that actually it's a smooth transition between them. And the optimal operating point might be somewhere in the middle. So all of these things are things that we would ideally get with this perspective. And the underlying principle is that continuity adds structure, and that's what we're trying to exploit. And by the way, please stop me with questions at any point. I prefer interactive talk, so any questions I'm happy to take as we go. So I already kind of alluded to this, but like, why does continuity help? Why does it matter? And I'm gonna make the point that it addresses each of the 3 pillars of limitations that I talked about before. So first of all, it gives us a broader design space. We have choices in between our original choices, and then we have entire trajectories that we can choose from instead of just isolated points. This gives us finer grain control in terms of model sizes, capabilities, storage that we can use for better utilizing the resources that we have. For downstream users, they can have a model that is essentially tailored and optimized to their own needs and constraints. And also, in many cases, as we'll see in this talk, these continuum perspective leads to much more efficient usage and storage of models. So instead of having to maintain repeated copies that share a lot of information, we can instead have a way to generate an entire family with the same atoms, but then spanning a full spectrum. Okay, so this is sort of to set up what I'll do in the rest of the talk. And I'm going to talk about such kind of limits in 3 scenarios. Continuum limits for datasets, for models, and for compute. So these are sort of 3 instantiations of the same principle with different flavors and different characteristics, but they all play on this idea. And then towards the end, if I have time, I will talk about more recent work that sort of bridges some of these ideas to work that is relevant to the SDM Institute in terms of decision making. All right, so how do we go about turning discrete datasets into continuum limits? So an example of this is this work with a former intern of mine at Microsoft, in which we started from this perspective of machine learning in practice, where you often, I'm missing some animations there. Okay. I think that's because of the Zoom sharing. I hope this doesn't affect all of that, but this is my fault here. So we start from this point of view that we have multiple data sets that are somewhat isolated. And then the idea is the first step towards getting something in between them is to define a geometry in that space, in the space of data sets. So for that, we use this idea of computing dataset distances based on a trial paper of ours, and computing the distances between a bunch of different computer vision datasets in this case. So we compute pairwise distances, and then I'm just visualizing here in 2D space. And this already starts giving some of the intuition of what are the kind of problems that we might want to solve with this approach. So if you look at this plot, you'll see that, oh, there it is. There's some gaps in this space. So by the way, here the distances are, this is a PCA MDS projection of the pairwise distances. So points that are far apart are high in distance according to this notion of distance that we propose. And you can see that there's some gaps in this space, in this manifold of data sets. So for example, there's a gap here, and there's a question of could we, given the data sets that we have, fill those gaps in order to improve generalization? So if we have gaps in the space, maybe if we can generate data that lives in that point and feed it to our model, train on it, then we will have better coverage of potential images that we'll see at test time. And maybe more specifically, if we know what target domain we have in mind, we might want to find the closest data set that can be somewhat generated by the data set that we already have, so that we can pre-train on that data set and then ideally have better adaptation to the target domain. So we're assuming here that for the target data set, we have very limited label data. For the training data set, we have much more. And the question is, can we find that point there? Can we find this point that sort of lives in the convex flow of the data sets that we have, train on it, and then, by virtue of being closest to the target domain of interest, we have better transferability to that domain. So those are the kind of things that we're trying to achieve here. So the way we do this is by leveraging the framework of optimal transport, which is a branch of math statistics that has a lot of interesting theory and applications, and in which I've worked for the better part of 8 to 10 years. I did my PhD focusing on optimal transport. And just, I'll abstract away the complexities of optimal transport, but I just want you to think about optimal transport as a framework to compare, match, and map between probability distributions. So through that lens and through that context, we can approach this problem by thinking about data sets as distributions. We can think of them as empirical measures that come from different domains. So now I'm going to think about each data set as a measure abstractly. And then I can have a combination of pre-training domains, and then I have a target domain of interest. And then what I'm trying to do somewhat formally is, as I said before, I'm trying to find the data set, the measure, in the convex form of my pre-training data sets that is closest to my target Q. And the way we do this is leveraging a specific version of optimal transport theory that is called generalized geodesics, which in essence gives you a way to trace paths between distributions in a parametric way, and specifically with respect to a reference measure, which in this case is going to be my target measure. So it looks roughly like this. So here I have my pre-training data sets, and then Q is my target domain. And then what we're going to do is we'll learn optimal transport maps between the target domain and all the pre-training domains. Those are the T maps. And that's really kind of the main thing that we do. Once we learn those maps, this generalized geodesic framework gives us a way to generate every possible data set that lives in that convex form. And I'm using convex here in quotes because the notion of convexity in probability space is a bit funky, but it's sort of a somewhat direct analog of convexity in Euclidean space. So here's an example of what one of those trajectories might look like. So here we would be interpolating between Q and P3. So that's the map that takes us from Q to P3, and you can see that how it sort of smoothly interpolates between these two data sets. Even though like one of them has 2 classes, the other one has 3 classes. In between, you get some combination of them. But this is what those kind of arrows look like between these data sets. And then once we have these maps, as I said before, we can essentially generate any point in that convex hull. And now the problem boils down to finding a weight vector, A, that corresponds to the distribution, the point in the convex hull that we're trying to find. I'm calling that PA. And the criterion for finding that distribution is it being closest in terms of basis and distance to our target distribution. So this boils down to a distance minimization problem. And by the way these geodesics are constructed, instead of having to optimize over the full space of distributions, we're really optimizing over the simplex, just the weight combination of the different domains. And there's some caveats and technical issues on how to do this efficiently. But once we do, we have a framework that allows us to do this. So what can we do with this kind of interpolation? One simple example on some semi-synthetic domains, MNIST and other simple data sets. here's one example in which we are assuming we have the 3 blue data sets, and we're trying to generate the yellow data set that is ideally closest to MNIST. And ultimately, that gives us better generalization towards MNIST. And then we run our framework, and then what I'm showing here, the top row is the distance between each point in the convex fold of those 3 data sets and the target domain. So this is sort of our design space, our navigation space. And this is the optimization criterion. And then the bottom row is sort of the downstream criterion that we really care about, which is if I were to train on that synthetic data set, the yellow data set, what performance would I get on the target domain? And here, each column is a different permutation of these data sets, with a different data set playing the role of the target domain. So the main takeaway here is that these 2 things are correlated, are highly correlated, and you can use this kind of justifies using this notion of distance as a criterion to choose our pre-training domain. And then we also have numeric experiments. We compare against a few different baselines, some of them using optimal transport, and we see that overall we outperform all the other methods that can do something like this. So yeah, with this, ultimately we can basically synthesize datasets at will with prescribed characteristics. This is maybe the simplest instantiation, which is the optimization principle is just distance to another domain, but you can think of adding other things that you might want there. You can add some complexity, some inductive biases, anything that you can express in terms of an optimization objective over distributions. You can add to your choice of loss, and then you can also optimize for that. Yeah.
So can you clarify the stages, pre-train, train, test time, like this kind of flow? Because the queue is given a test time, right? But you talk about training as well, and we talk about pre-training. So can you clarify that?
Yeah, sorry. Here, there's really no, pre-training, and there's just training and fine-tuning. So here we train on the synthetic data, the yellow one, and then we assume a limited number of labeled samples from the target domain. So we do a few shot fine-tuning on the target, and then we evaluate. So it's a simpler, just train and fine-tune setting.
Okay, there's no foundation model being trained.
There's no this is a very simple neural network architecture. I think we're using a simple CNN with a couple of layers. Yeah. So this is mostly to show that this is kind of doable at a small scale. I must say the optimization is not trivial. So scaling up to foundation model size models is sort of something that we yet have to do. Other questions here?
So in this case, you look at what if you just learn representations from the other data sets and then in short transfer?
Learning, yeah. So if you use the other data sets to pre-train, yeah.
And then just train, fine-tune the last layer or something.
So we compare against pooling all the data sets, for example. We have baselines that cover basically everything else you could do, every other simple way you could use all these data sets. So it includes combining all your data sets and training on their combination, training on each individual data sets, and then comparing what you get if you had used essentially the corners of the polytope. And in all those cases, those are superseded by training on a combination. Going the representation learning route, that could give you a different approach. At this scale, with this kind of models, I would argue that that's probably not something you want to do. But yeah, there's still a question of, you could still play a similar game in latent space. And even with those representations, those still will imply different distributions now in a latent space, right? So there's still a question on, if I train on either, a single data set's latent representations or their combination, or instead a synthetic interpolation between them, which one would be better? And I believe we don't have experiments on that. But yeah, that's a good point.
What would be the procedure to generate a new sample? Is it that you take images from each of these and then sort of use the scheme map to generate a new one?
Exactly. Yeah. Yeah. So the generation happens exactly like that. So you sample from each of the coordinate distributions, at least the ones that are needed for your combination in your weight vector. But assuming you have a non-zero weight in all of them, you would sample from all of them, and then you push each sample through the map. So that sort of gives you a push forward into the middle distribution, and then that's your synthetic. The combination of those is your synthetic data set.
if we are talking about like filling the gaps in the distributions, right? So like isn't filling the gap also creating dependencies between the different distributions?
In what sense, dependencies?
Because we are sampling from the existing data set and then using that to create a new point. So isn't that creating like it depends on the data that you already have?
Yes, absolutely.
So there is a dependence between the data that you have and the new data that you're generating.
Absolutely. Yeah. So this is really kind of bottlenecked by what training data sets you have, right? So in a sense, you're limited to generate things in the convex hull that are, interpolations between them. If you have few domains or those are, poor quality, then this is for sure gonna propagate into what you generate. So there's no magic happening here. You're essentially finding smart ways to combine them in a geometrically meaningful way. Yeah. Okay, so moving forward in terms of takeaways, the idea here is, we are essentially embedding these discrete points, data sets in a continuous space, the space of distributions. And then once we're there, we can use optimal transport to give us a geometry between them and to basically formalize all these operations in that data set space. One sort of analogy that I like to think about is, whereas in classic machine learning, we typically think of the space of samples given a data set. Here, this allows us to instead think abstractly as the space in terms of the space of data sets, where each point is an entire data set. And then essentially what we're doing is we're defining operations in that space. Sum, interpolation, combination, deletion, addition, anything that you can think of in sort of Euclidean sample space, you can try to think what would be the analog in this data space. And this gives us sort of access to the in-between domains. Again, this is sort of bottlenecked by, but whatever you have, you're going to be in between them. So there's no kind of knowledge outside the box being created, but it's giving you sort of additional statistical power by accessing those intermediate distributions. And besides, the sort of downstream usage, I think this is also a useful tool to understand the nature of the data sets that we already have. Are there gaps? Is there anything we need to take into account before we launch a big large-scale training on those data sets? All right, so switching gears a little bit, we're moving now from data sets to models. And I'll start with this project by my student, Sarah, who was very interested in sort of practically in the problem of user tailoring of language models. So if you have a user with different preferences, how do you provide a model that is sort of tailored to their own preferences and constraints? And how do you do that in an efficient way without having to retrain a model for every different user? So that was a practical question. The more abstract question was thinking about the connection between this data space that I talked about before in a hypothetical space of models, and what are the relationships between them? So where are my manifolds? There they are. So thinking about imagine you have all these data sets and you train or you fine-tune a language model on each of those domains to make it a specialist on law, math, code, whatever. You have those 4 models. And then after this stage, maybe there's an additional domain that lives in between them that you would want your model to be specialist in. So you would want a model that is sort of fine-tuning that yellow data set that I didn't have, or the model provider didn't decide to fine-tune a model on. So the question is, given my already pre-trained models, is there a way I can recover a model that would have been fine-tuned on that hypothetical intermediate domain? And can I do that in a sort of efficient way by reusing as much as I can my existing models? So that was the driving motivation of this. And as I said, sort of there's an interesting kind of deeper question here, which is how do these two spaces relate to each other, the space of models and the space of data sets? So the building block that we'll exploit here and sort of the main technical aspect is actually something very simple. It's this idea of model swooping from this paper by Wertzman and colleagues. If you're not familiar with it, it's a super simple idea. You take 2 pre-trained networks, and then you literally just do linear interpolation between their weights. At each layer, each block, this assumes, of course, if you have the same architecture, trained on, let's say, different domains, and then you do a weighted, typically just half-half combination of their weights. that gives you a new model, which surprisingly performs very well. So when this paper came out, it was sort of a big surprise to the community because a priori, there's no reason why this should work, right? It's not clear why this should work at all. And it works surprisingly well. In that paper, they show that sometimes the combination is even better than the individual parts. So if you have different models that are, they branch out and you have different seeds, trained on the same domain, so they're all sort of trying to optimize the same objective, but then you have, these multiple copies, and then you do this kind of weight averaging, you get the interpolation is better than the combination. So surprising phenomenon has been replicated many times, and there's a lot of questions of why this happens. It relates to the linear representation hypothesis. There's a lot of interesting work trying to explain this. In our case, instead, we're trying to exploit it in sort of novel and interesting ways. So the setup is the following. We'll assume that we have a base model, like a base LLM, and then we do LoRa fine-tuning on a specific domain. So let's say this is a model that is being fine-tuned to produce either more complex or simpler language. And then we have two data sets on polar opposites of this. This could be, middle school English, and this could be, archive English. And then we fine-tune models on the two opposite ends of the spectrum. And the fine-tuning is done in a parameter efficient way. So we use LoRa. These are the LoRa updates. So once we have those updates, we now have two models that sit at opposite ends of the spectrum, the minus and the plus I models. So we do this, and then already with this and with the model soup approach, we can in principle generate every model that lives in between them. So we can, gradually turn the knob of complexity by playing with the weight interpolation alpha here and move to, each side of this spectrum. So that already gives us a notion of interpolation, right? It's interpolation within the axis that I'm fine-tuning here on. But then we can do this across multiple different behaviors, domains, tasks. So this could be complexity. One of them could be verbosity. The other one could be humor. The other one could be mathiness. So let's say we do this for a bunch of different domains. And then for each of them, now we have these, opposite sides of the spectrum. So we have, in this case, a total of 10 LoRa weight updates. Now these define a space, a category that we can also interpolate between. So we can choose now lambda interpolation update that put us somewhere in that pentagon in this case. In this way, it sort of defines where we want our model to specialize, right? Do we want it to be more, pay more attention to the mathiness constraint versus the verbosity constraint? So we can play with that. And then with the alpha weights, we can say within the mathiness, I want it to be PhD level math or, high school level math, whatever. So this theta star is now our interpolated set of weights. And again, this is just literally linear combination of weights following the model soups recipe. And now the big question is, okay, this sounds, sure, you can do that, but does it actually work? How can you prove that it gives you something reasonable and meaningful? So the first thing that we do is to verify that the combination sort of does what it's supposed to do. And for that, we train classifiers for each of these characteristics, the 5 characteristics that I talked about. And then we look at what the score is for each of the characteristics as we vary the weight, the alpha weight. So remember this polarity score. I would have for math, for example, or let's say for formality, I would have a verifier model that gives me a score of how formal versus informal the language is. I plot that in the y-axis as a function of my knob alpha. And if you recall, I showed how alpha is really defined between 0 and 1. 0 is I have one side of the spectrum, 1 is I have the other side of the spectrum. This is the interpolation regime, the reasonable interpolation regime. And then we can see that we actually get very smooth interpolation that correlates very well with what a verifier, a classifier would say. So this shows that the alpha knobs do what they're supposed to do, and they do it in a smooth and meaningful way. And interestingly, you can turn the knob beyond its reasonable value between 0 and 1, and then you can start to try to extrapolate beyond what you had in your fine-tuned models. So this is, just to show a zoom in on each of these each of these characteristics. So this is in the interpolation regime. The line is our set of interpolated models. And then the other verification is what would have happened if I actually fine-tune a model on that combination. So for an alpha of a half, let's say, I now fine-tune a model as verification. This is just as an oracle judge. I train a model on a mixture of 50-50 of complex English and or formal English and informal English. And then I compare what that model gets versus our interpolation. And here the amazing aspect is that we very closely recover those intermediate models. So even if we had gone through the trouble of actually fine-tuning a model that is targeted for that combination, we would get something that pretty much captures this attribute in the same way. And this happens across all the attributes that we test. So this is ultimately the test, right? Like you want something that saves you the trouble of actually going through fine-tuning and give you something that roughly recovers what you would have gotten if you actually go through that without actually training. So that is the interpolation regime. This was nice. It was kind of what we were expecting, but then we started playing with the knobs and going beyond interpolation into extrapolation. And there you can see, here that even if you start extrapolating a little bit, you still get some meaningful, smooth extrapolation of the properties. So we go beyond what you get in the interpolation regime. So even in reasonable extrapolation, you get a behavior that scales reasonably. At some point, if you turn the knob too much, things break down, and then you get garbage out of the model. So there's a limit on how much you can push things beyond their pre-established boundaries, but it's also kind of cool that this simple combination allows you to go beyond what you had in your fine-tuned models. And again, that says a lot about directions in weight space between polar opposites, and I think there's some conjectures on why this happens, but it's nice to see it in practice. Okay, so any questions on that project?
It didn't look like humor degraded from that stage.
Yeah. Yeah, that's a good observation. So that's interesting. Yeah, I don't remember exactly what the extra humor samples look like, but it could be that there's just some more tolerance. It could also be that the fine-tuned model, what we use for the +1 side, maybe is mildly humorous, but not extremely humorous. So the model in its pre-trained data still has seen things that are more humorous than that, and it can still do this extrapolation. But yeah, it's interesting that it doesn't break as fast as the other ones. Yeah, simplicity is the one that breaks much faster. Yeah, in the back.
For instance, like more hallucinations or the perplexity drops or any one thing you lose really, wasn't it?
Yeah, so we did perplexity checks. We have those plots in the paper, and eventually it breaks as well. So here, these are characterized by your perplexity breaks down. So you're just generating garbage. So there's a limit to how much you can do this. The first part of the question was hallucinations. We haven't tried that. That would be interesting. Yeah, we didn't look into hallucinations or other sort of more sophisticated behaviors. But yeah, I will be curious to see if this has a direct effect on hallucination, and also if you can reduce it with a hallucination model as well.
And the related literature is steering.
Yeah, activation vector steering. Yeah, so that's also connected. We make reference to that. I think they're complementary approaches. This is directly operating on weights, and that's operating on activation. So, but maybe there's something that can be done in combination. Yeah. I think there was another question.
So you said that the interpolation is almost similar to the fine-tuning result.
Yeah.
I was curious, like, how are you exactly getting that fine-tuning result and how you're comparing them?
Yeah, so for these points, the fine-tuned models, we're taking, so, this is kind of, you have to do some assumptions here, but we're trying to replicate what a model that sits between our two initial fine-tuning data sets would look like. And our best guess for that is one that trains on a mixture of them. And the mixture is at the rate of the alpha vector. So for example, for this point, I would take 50% of my fine-tuning data would be from the simple data set, 50% would be from the complex data set. I train in that mixture, and then I check what the resulting model has in terms of performance. There's other ways to do it. This is not the most sophisticated version. There's maybe finer grained kind of interleaving methods. We tried kind of the simplest thing you could do. Yeah, that's a good question. Yes.
It's not really intuitive how you would do like a Wasserstein geodesic between text data, right?
Yes, this is a question that has bothered me for many, many years. Yes, so that's there's no Wasserstein here. We're not doing any Wasserstein. Like there's no there's no geodesic interpolation here. But yeah, it's variable length data is tricky for many reasons, and also it's discrete, so it has all sorts of complexities. We have some results in some work that I'm not mentioning here, but all of those operate in some latent space. So once you have a reasonable embedding with reasonable geometry, then you can do OT, but you lose a lot in that process. So yeah, we have some ongoing work in that direction, but yeah, that's one of the main limitations of applying this amazing toolkit of OT to text data. Yeah.
I have two questions. One is, I really missed this, but how do you measure the different aspects of the model? Like,
The y-axis here?
yeah.
Yeah. So we train a verifier. We train a classifier on the data itself, and it has to classify whether it's domain A or domain B, and then we take the score of the classifier as our metric of how well you're targeting that. So it's a simple classifier. I don't remember the details, but I think we're using the base model and then fine-tuning it with a classifier head. So we stack a binary classification head on the pre-trained model, and then we use that. All right, so I'm gonna move forward to another project, again, by the amazing Sarah, that plays with the same idea, but now across different model sizes. So this is work that was recently accepted to iClear. And here the motivation was slightly different. So the motivation was this, discrete choices of model sizes. So we're all familiar with these kind of plots. We have different models that we can choose from different model families, but there's still large gaps between them, right? So this is like a 30 billion parameter gap. And sometimes we wish we had the model that lives in between, right? Or we wish we had all of them, and then we could do different things with, different points in that region. So our question was, can we somehow use those pre-trained models and get the models that live in between them? And we would want to do this with minimal training, right? If we end up spending as much flops as it would take to actually train that model, then there's no point. Like if you do this, it should be in a way that is very compute efficient. So why would we want to do this? As I said before, there might be compute constraints, GPU size, and you ideally want the largest model that you can fit in your GPU. There's also an interesting aspect of science of LLMs. Many of these sort of phenomenological studies and scaling laws and those kind of things are based on very sparsely sampled models. So being able to at least simulate the points that live in between could give you something smoother, and maybe some transitions that you're missing because you don't have those points. You could get, at least in a semi-synthetic way. But of course, pre-training all those points in between is very computationally expensive. That's the reason why Meta, OpenAI, Anthropic don't release every possible model size. You could distill models, so that's what is kind of in vogue these days. But still, this would require distilling at every possible size, so it requires a lot of commitment. You need to know which size I want, and then put a lot of distillation into that. And then if I change my mind and I want a smaller model, there's nothing I can do. I have to restart from scratch. And so the question is, can we somehow bypass that? And the answer is yes, through this extremely simple but surprising phenomenon that Sarah discovered while actually working on a slightly different project that we call boomerang distillation. And it's this phenomenon where we can create those intermediate models at the cost of just distilling one model. So how does that work? So we start with our teacher model. That would be the largest, let's say the largest model in the family, or whatever model in the family that's kind of your upper bound on size. And then you choose a small size that is going to be the other side of the spectrum, and then you distill to that model. And this process involves pruning layers and then doing a distillation drive. So we prune layers of the model. So we're compacting it, compressing it, and then we have a small model. So far, no surprises. You can do this. Our distillation and pruning process has some nice aspects to it, but the surprising aspect is once you do this, you can start adding back layers without doing anything, and just adding them back, and then basically trace this path back towards a big model. And those intermediate models are quite decent. So that's the boomerang distillation phenomenon. So how does this work exactly? So we start by mapping the layers of the teacher to student layers. So we choose a subset of layers of the teacher, and we assign them to a block. So that block gets assigned to one layer of the student, and then we initialize that from our copy of one of the teacher layers. And then we have a distillation training with small amount of data that has an objective that tries to preserve perplexity while also aligning the layers. Intuitively, what we're trying to do is now we want this layer to somehow play the role of the composition of these two layers. There's going to be an alignment loss at this point that says, as a block, this should be similar to this, and we do this across all the different blocks. And this ensures that not only end to end, the model still behaves like the big model, but at each threshold, each checkpoint here, not checkpoint, each cutting point in the depth of the model, it still behaves like the teacher model. So that's the distillation phase. And then once we're interpolating, whenever we want to add new layers, we just recover and copy over the layer that we hadn't used before. So we copy it over. We call this patching the layers. And then depending on how many layers you patch, you can recover all the intermediate models between them. So it's an extremely simple procedure. And yeah, the only step that involves compute is this one. So there's one distillation, and then this step is for free. You just add as many layers as you want. Okay, so some experimental results. This is with Quen. We start, so the 4B model will be our teacher, the big model on the right, and then our distilled model will be a 2B model on the left side. And then we'll generate basically a bunch of models in between 2B and 4B. And here we're plotting accuracy of those intermediate models and a combination of tasks. Some of them involve classification, some of them are measured by generation. And then I'm showing three types of interpolation. So blue is our method, the boomerang interpolation. The star is the performance of the teacher, the big model. The triangle is the performance of the distilled model, the smallest one. And then everything in between are those synthetic models. So the first observation is that you get nice smooth interpolation behavior between them, right? So you get this sort of path that recovers slowly the performance of the teacher model in a gradual way. And then we're comparing against two baselines. So one is what happens if you just naively prune layers. If you just drop layers from your teacher, that is terrible. Like that doesn't work very well. You very quickly degrade and you lose all your performance. And the other baseline is just doing distillation without this teacher initialization and patching. And again, that doesn't work. And it shouldn't, because there's nothing that is grounding the model to be similar to the teacher model. So these are two of the simplest naive ways you could do interpolation that clearly don't work. We have results that show similar smooth interpolation behavior across different model sizes, different datasets, different benchmarks. This is for Quen, Pythia, and Llama models. So similar behavior. And here's what gets interesting. So similar to what I showed you before, where the synthetic models would actually mimic or replicate models that you actually fine-tune in those points, we can play a similar game here. And we can ask, what would happen if we actually go through the trouble of distilling models for intermediate checkpoints? So those are the triangles. So each triangle is going through its own independent distillation run at a targeted specific size. So of course, this is 1, 2, 3, 8 times the compute of our method, but only does 1 and more because these are library models. And then you see that you pretty much recover their performance again. So our synthetic distillation models recover, and in some cases outperform models that are distilled at that size. So again, in sort of lower regimes, we recover performance, and sometimes in larger size regimes, we actually outperform those models. So this was the most surprising result of this project, that you can actually for free, get a model with equal or sometimes even better performance of a model that is specifically targeted to a size, while having all of them at your disposal, all the intermediate points, all the blue points. And again, we have results that show this across different model sizes and model classes. This is sort of ablation. I'm not going to go through the details, but we have 3 losses in our objective, and then we're trying to understand what is the contribution of each. And the answer is you kind of need all of them. But the interesting thing is that this alignment loss that I talked about that keeps the layers kind of grounded and matched across the sizes, that's very important, especially in large regimes. Without that, you get this loss of stability in your interpolation. And also another kind of bonus, super interesting result is we said, okay, what happens if we take a model that we didn't distill ourselves? This is a model that was already existed. It had been, released years prior, distilled BERT. And then we tried to do the same with this model. And we see that even in that case, we get this, interpolation behavior. So this kind of shows that even for models that, we didn't even touch the distillation, we can get something similar. And the principle at play here is that distilled BERT was distilled with different laws, but with similar principles as we're doing. So it shows that as long as you're sort of getting that loss right, you can do this type of smooth interpolation. And here we compare against some more sophisticated, yes.
I probably missed this, but you're doing distillation and then patching as well. So in what part are you like training the model again on the data, or are we not doing that?
We're not doing that. We just do it for the the smallest model. Big model, you prune, you have your small model, and then you fine tune.
Okay.
So that's with the distillation loss, with a combination of those losses. And at that point, everything is frozen. There's no training. So if we want, the intermediate model, we just take the model that we have and we add back. The patching is compute free. We just literally inject the layers in the corresponding places, and then you do your forward inference.
So then in what sense, like, are we saving on the compute, like distilled BERT versus your method? Like, what are we saving in terms of compute?
So what we're saving is that if you want a model of a specific size, you don't need to distill for it. The distillation happens once, and you're amortizing the whole trajectory. So you don't need to, if you're trying to service multiple models to different users, I give you a 4B model, 6B model, I get all of them for the cost of just the smallest one. Yeah.
Or somebody else is still going to do this, but like, can you tell us why you think this works?
So I think the principle is that distilled BERT also has something like an alignment loss. And I think this is the key. So it combines a logit typical distillation loss, and then it has some alignment term. And I think the combination of those two is what works. But surprisingly, that is not crazy. Like many distillation methods do that. So I think what is at play, and they also initialize from the teacher layers. Yeah, so I think the principle is it's a combination of you're initializing from your teacher layers. So you essentially have that information already there. And then you are in a sort of parsimonious way, making minimal edits so that the building blocks that you had before still work in a way that, when you add back layers, you're not, you haven't modified the weight so much that when you add things back, they're not compatible. I think it's all about compatibility. This distillation sort of ensures that the individual blocks remain compatible, even if they add back other components. It's a very hand-wavy explanation. I wish I had a better one, and it's something that we're still, trying to understand better. We have some follow-up work that is trying to stress test this and understand when like the paper, the way we phrase it is, technically there's nothing super interesting happening. It's more like the phenomenon is there, and the paper is like trying to understand when it happens and when it doesn't. We were hoping that we would see it just happens in a small sliver of settings, and it doesn't happen in many others, but we kept accumulating settings in which happens. So yeah, I think still it's an open question, and I think there's a deeper explanation in terms of geometry of those weight spaces. Was there another question? Yeah.
Just a super one. Am I correct in thinking it does not matter like what order you patch when you're patching which layers you add back in with?
It does matter. That's a great question. So that's in the paper we have some results that we do two types of, in this version of the paper, we do two types of ordering, back to front and front to back. Both of those give you something reasonable, but if you do it in a random order, it doesn't work well. But then you can also think, is there an optimal order in which I can do this? And does it depend on the task? And that's sort of something we're looking at in ongoing work. But that's a great question. It's the answer is subtle. It does matter, but we don't fully understand why. Yeah.
What if we order in terms of the layer alignment loss?
Yeah.
Depending on which.
That's one of the things we're trying. That's a very good idea.
And the second question was, how far can you push this? Like, how far can you distill and still get it?
You're asking all the right questions. So we're also experimenting with that. So we have some preliminary results that we submitted for workshop that show that you can go way, way beyond what I showed here. Here I was kind of going to 50%, like from 4B to 2B. You can go way smaller than that. Again, of course, the smaller you make it, then you start running into that model size might not just be enough to get a good performance in the task. And at that point, you lose your measurement. Like you cannot distinguish different levels of good or bad at that point. So you need different benchmarks. But yeah, that's a very good question.
Sorry, just one more question.
Yeah.
So let's say we are patching and we patched enough that one of those blocks is completely the teacher block now.
Mm-hmm.
So do we just copy all the teacher block weights, or do we let one of them remain the student block weights and the remaining ones are the patch ones?
Sorry, if I understood correctly. So as we, so you do this in a block-wise order. So as you kind of convert that block, you start adding all the blocks from that, all the layers from that block. So this goes back to the ordering.
Okay.
Respecting block ordering is also important. You can do it without, but the smoothest interpolation you get is if you take one block at a time, you fill it out, and then now that's fully patched, and then you go to the next block, and then you do it like that.
So like moving from one point to the next is one block being completely replaced from the student to the teacher.
Yeah, one layer at a time. So we still have the resolution one layer at a time. So that's our granularity. But the way you do it is, you choose this block, and then you do, I already had one, the one that I had copied over, and then I do, let's say, 2, 3, 4. And now that block is fully recovered. And then I go to the next block, and I do, 3, 4, 5. Each block can have a different size. So there's also different ways you can cluster them and find those blocks. So there's also lots of nuances in how you can do this. We're still exploring what the best way of doing it is. In the paper, we do sort of the simplest thing you can do in each of those settings. Yeah. All right. So, takeaways here. The main takeaway is you can now expand the range of models that you have at your disposal at the cost of one distillation, and without any additional training, you can get intermediate models. Kind of summarizing the discussion that we just had, important thing for this to work is that the student layers need to be initialized from the teacher, and then you need to have this distillation loss that sort of recovers, addresses the fact that now you're missing some layers and sort of patches that in a geometric alignment way. Okay, so for the third, how am I doing on time? Okay, so I'm running a little bit short on time. I'm going to go through this a bit fast, and then I just want to end with connections to decision making for the AI-SDM people here. So we talked about models, data sets, models, and then sort of the third axis that we have in machine learning is compute. So this is a project by my student Jonathan that actually builds off of work that was started here at CMU on deep equilibrium models. So the motivation here, and I guess it's the same motivation that the deck authors had, is that having a fixed architecture implies fixed compute, right? You have a fixed number of parameters, so every forward pass will have the same cost, essentially, ignoring variable sequence length. But for a given input size, you have fixed compute. And that is suboptimal when you're dealing with inputs of different complexities. So in language models, you can imagine if I'm asking my model a IMO level question, I would expect it to spend more compute than a elementary school math question. And we have now in the last couple of years this whole branch of methods that try to address this issue by doing test time compute, adaptive test time compute. But Yeah, so the motivation is the same. Not all inputs are created equal. You want to ideally spend different types of compute and optimize the compute that you're spending on each type of input. And here, with this kind of fixed rigid architectures, it's hard to do this without, the different training tricks. Like just on an architectural perspective, if you need higher accuracy, you would want a deeper model just for that question, but you would need to train a larger model for that. If you need a faster inference for a simple question, you would need a kind of a new model that is trained at a smaller scale. So again, similar principle. We're stuck with the choices of whatever the model provider decided, and there's no simple way to change that once we have the model in our hands. So this is kind of where deep equity models come in. I'm sure many of you are familiar here with this paper, but if not, it's a different kind of architecture from Zico's group that plays on this idea of fixed points. So instead of having a parametric model that has explicit computation at each layer, like a function that is applied at each layer, you define the output of the network as implicitly as the solution of an optimization problem, a fixed point system, or something else. So it's sort of a different way of thinking about computation. And here this diagram is trying to show that. So instead of having a sequence of L layers, you instead have this sort of equilibrium layer. And what you're saying is, I want my outputs to satisfy an equilibrium condition, f of z equals z. And then I'm going to run some optimization as many times as I need, as many iterations as I need to find that fixed point. And here the idea is that if the input is simple, my solver might take fewer iterations to get there. If the input is complex, it might take more iterations. And this sort of variability is sort of native to this architecture. It can take as many iterations as it needs to find the solution. So this sort of for free gives you this notion of adaptive compute. So it's a very neat idea. This is, so this is, sorry, I should have shown this slide before. This is just a restatement of what these layers do, comparing an explicit layer to an implicit equilibrium layer. So the output is defined as the fixed point of this function. And this paper is very interesting because it draws this analogy to infinite depth. When in principle you have something that can iterate ad infinitum, you have in your hand something that can simulate an infinite depth neural network. And in particular, it can simulate a neural network of any depth that you want. So it has this, again, this nice idea of taking a limit, a continuum limit of discrete number of layers into something that is essentially semi-continuous. How are these trained and used? There's some intricacies. Training them is not trivial. In order to find the output to do the forward pass, you're finding a fixed point. The cool thing is that you don't need to store all the intermediate activations that go through this box. When you're doing backprop and you need to go back, they show in the paper that you can essentially run an equilibrium in reverse. So this is memory-wise, this is very efficient, right? Because if you have infinite depth, you could think that you have infinite number of activations, and then the more you run, the more you collect activations. That's not the case. You can forget all about intermediate activations, just keep the last one, and then when you need to backprop, you go in reverse. So you've solved this backward iteration with an implicit gradient step. So the technical details are maybe not too important, but it's a very cool paper, and it has exactly what we wanted. The limitation is that the way they instantiated these models assumes fixed inputs, images of a fixed shape and dimensionality. But as we were discussing before, there's many types of inputs that are variable length. Text sequences, point clouds, especially distributions that are represented as point clouds. Those don't admit this fixed shape size, and they also have some geometric aspects. A point cloud is really naturally represented as something that is permutation invariant. Normal DEX don't have that. So our question was, is there a way to take this idea of DEX, but apply it on much more general classes of data? Sets, distributions, graphs, especially variable size types of data. So that's what we do in this paper. And again, the machinery is similar to what we do in optimum transport. We think about point clouds and sets as empirical measures. So from this point onward, I can think about my data set as just a measure row. And then we basically just need to restate the deck setting, but now for probability measures. So the data is a measure. There's this latent point that we iterate, the measure mu. And then our layer is a distributional analog of the deck layer. And then depending on the task, if we're trying to do point-wise classification or point-wise completion, we have a different final layer in our network. So that's sort of the architecture. The principle is the same. We need to find a fixed point. But now we're trying to find a fixed point in probability space. So things get funky, and that's where kind of the main technical aspects of the paper come in. I think I'm going to skip through this in the interest of time. I'll just say that there's distributional analogs of everything that is done in that paper. And what you end up with is mathematically very interesting. It's a gradient flow in probability space. If you haven't heard of gradient flows, they're a continuum limit of gradient descent. You can define them in Euclidean space. You can also define them in probability space. And these kind of flows appear a lot in optimal transport because they describe trajectories and geodesics between distributions. So there's a beautiful connection here to optimal transport and PDE theory. For our purposes, what it gives us, it gives us a way to solve that fixed point iteration that we need. So this is kind of our objective. So this is the instantiation of the compute of the network. We're trying to find a measure that is a fixed point of this operator F. In the Euclidean case, what we would do is we would subtract this point from here, make it equal to 0, and solve that as a root of this system. For measures, this doesn't really make sense. Like, this is not well defined, and I cannot take just the difference of measures trivially. But instead, what I can say is something analog is I want the distance between those two things to go to 0. What distance you choose depends on what you're trying to achieve. We use an MMD, maximum mean discrepancy, which makes the flow well behaved. And with that, we have our objective. And then finding the fixed point boils down to solving this gradient flow in probability space. So if you're interested in the math, I recommend you to check out the paper. And also, I think there we cite a lot of very nice surveys on gradient flows for probability measures. We end up with this kind of architecture. I won't go into the details, just to say that in order to get this notion of permutation invariance or equivariance, we use transformers without positional encodings, similar to set transformers and things like that. And just a couple of applications of what we can do with this. We try it on point cloud completion. So here your input is a point cloud, and you need to recover the missing points. We can do that. And this is comparing to some state-of-the-art models that are targeted to this setting. Performs very well against these. We also try it in classification. Here the task is you feed the point cloud, and then you try to predict a class. And we also get nice results in that setting. So these are kind of practical architectures that can be, actually used in practice for this kind of data. So just a couple of takeaways here. We developed this architecture that generalizes DEX, equilibrium models into distributional settings. It can handle variable size inputs like point clouds. We haven't tried it on text. There's the question there, you don't have permutation invariance, so we would have to do something different. And it has beautiful connections to dynamic OT and PDEs. All right, so in the last 4 minutes, I'm going to talk about some recent ongoing work that ties together to the themes of AI-SDM. And here, the point that I want to make is that decision-making, especially these days, involves data in many ways. So being a data-centric machine learning group, we care a lot about data. And in the context of decision-making, we care about two different directions. We care about data that is involved in decision-making processes, especially when there's AI involved in that process. So here you might wonder if I'm in a setting where AI is used for some downstream decision-making, how do I choose data sets? How do I combine them? How do I compare them? All these questions that we asked before, but now in the context of decision-making. But there's also the question about decisions that we make every day about the data that we use in our models. So I already sort of touched on that before, but there's a lot of decisions that us machine learning researchers, but also practitioners make on a day-to-day basis when they want to deploy a model for their application. And it's not always clear how to go about answering those questions. This space is full of heuristics, and ideally, we can sort of abstract some of these methods, formalize them, and make them much more reliable. So we're interested in both of these directions, and I'm going to give one small example of each of those. And again, playing on this principle that discrete choices can be made more tractable through a continuous view. So the first project is sort of on the data for decision-making direction. And this was led by Paula, who is affiliated with AI-SDM. And this was in the context of decision-focused learning, and specifically predicted, then optimized. So if you're not familiar with the framework, it's an interesting sort of combination of machine learning and optimization that considers this kind of pipeline. Ultimately, I'm going to make a decision, but the optimization problem that I have to make, that I have to solve to make a decision, depends on some estimates that I need to learn. It could be the costs that I need to estimate. If you're solving a shortest path problem, it would be predicting the cost or the traffic along each of those edges. So there's a learning component, and then there's an optimization component, and these work sort of end to end. And the overall summary of this literature is that if you solve these in isolation separately, this is suboptimal. You're better off learning them in combination end to end. So that's sort of what summarizes the field of PTO. So in our case, we arrived at this problem with similar questions that we had in previous work, in the context of having multiple data sets at our disposal and which one we want to use not being clear. So again, the goal here is transferability prediction. Let's say somebody has already trained one of these models on some domain A, but I really want to apply it in domain B. Which model should I choose from pre-trained models? Which one is more relevant to my task of interest? And we take a similar approach. We try to characterize task similarity through optimal transport, geometric distances. But the problem is that those distances are not designed for the decision-making setting. So they completely ignore the decisions that are attached with each data point here. And just to be a bit more concrete, the instances in these data sets are triplets of a feature, image, or cost or whatever. Sorry, the descriptor of the edge in a shortest path. Then the label associated with it. This is what we're trying to predict in the learning phase of the problem. And then there's a solution. There's a decision of the optimization problem. So we have these triplets. In classic notions of data set distance, only take this one. The one we proposed in prior work considers labels, but we're still missing the decision component. And the question was, how much does that matter? How much can I gain if I actually model decisions in the way that I compare my tasks and my data sets? So we did that, and we did it through a fairly simple way, which is extending optimal transport to now essentially model decisions. So the point-wise distance between two data points now will be a combination of a feature distance, a label distance, and a decision distance. Of course, here the crux is how do you define a notion of a decision distance? We explore different ways of doing it, but roughly we compare them in terms of their downstream performance. So for the same, let's say, costs, I compare two different solutions of my optimization and compare those values. And the difference between those values is what I'll call the decision quality disparity. And that's what we use as a notion of distance between decisions.
Sorry if I missed this. What assumptions are you making on how decisions are structured in this setting?
Yeah, that's a great question. So depending on the nature of the decisions, defining this might be easier or harder. So here we're dealing with typically discrete decisions. So they're either a class or they can be a sequence of edges. So the advantage of this perspective is that regardless of the object, you always have a downstream cost associated with them. So you don't need to define a geometry between the objects themselves. I don't need to define an object between graphs. I can just look at whatever the downstream performance is. This will always be available. So this is the most agnostic way of doing things. But you could get improvements by being a little bit more fine-grained in how you compare your decisions. If they're trees, you want to do something like a tree metric or something like that. And the result says that this notion of distance that is optimal transport, taking this as an ingredient and then lifting it into a notion of distance between tasks, is highly predictive of this transferability that we care about. So here the x-axis is the data set distance that we compute, and then the y-axis is the change in performance, the relative transferability across task A and B. And here the idea, the goal is that you want this distance to be predictive of the task, because this is what you will use to choose the data set that you will sort of transfer from. And here we compare a decision agnostic version of the distance, what we did in prior work, with a decision conscious, decision aware version of the distance. And overall, you can't really see it there, but if you look at the R-squareds, you can see that incorporating decisions make this much more predictive, and in some cases, dramatically so. So the overall theme here is injecting decisions into the geometry of how we compare data sets and comparing them, under this induced decision geometry. And then finally, the last part I'll talk about is this recent preprint that we have, again, with Paula and my postdoc Nihal, who's also affiliated with AI-SDM. And here, the motivation was a lot of times in machine learning, when we're fine-tuning, we need to choose a data set to fine-tune on, and specifically in the context of instruction fine-tuning for LLMs. You have this problem where you typically don't want to fine-tune on everything. You have to kind of curate your data set. So you have a pool of examples that you can choose from. Most of them are not relevant for your task. And then you have to find a subset that is as relevant to your task as possible. And you do the fine-tuning on those. So this is nothing but a subset selection problem from a candidate instruction pool. And you're given a small amount of queries that come from your task of interest. And then you're trying to select a subset of the pool that is as similar as possible to the queries. So again, this has the flavor of sort of distribution of distance minimization. And you want to maximize the downstream performance once you fine tune. And the overall message from this paper is that this literature is very messy. It's fragmented. Things are very hard to compare. There's no apples to apples comparison. Basic baselines like random selection are never included, and in some cases those outperform the models. So this was a very frustrating project because we spent most of the time actually trying to clean up and do a apples to apple comparison before we could even propose a new method to do it. So the overall message is, despite the mess, there's kind of a unified way to think about this that we proposed that basically disentangles the two main things that go into these subset selection methods. The first one is, how do you represent your data, your instruction samples in this case, and then what selection algorithm you use on those representations. So through this lens, now you can take all the methods that exist, find out what they do for one, what they do for two, and then you can mix and match and try to compare them in an apples to apples way. So the overall findings is that it's a great picture. So most of these methods, if you actually look at the objective that they're optimizing for, it's very weakly correlated, and in some cases not correlated at all with performance. Some gradient influence type-based methods, in some cases, are correlated. But the surprise is that for most of these, in many cases, a random subset does just as well. Which is, yeah, it's frustrating, but I think it's a call for more rigor in some of our experiments. But this is it maybe this is an overly pessimistic view. We do have some settings in which we show that you can actually get an advantage from doing smart subset selection. One of those is we propose an optimal transfer-based method that performs well in some regimes, better than random at least. But also we show that we can sort of understand and explain some of these failings by understanding all of these methods as trying to do approximate distribution minimization between the queries and the selected subset. So there's also kind of an interesting connection to Wasserstein distances here. But overall, yeah, the lesson is that we need much more rigor in how we do these evaluations. We have some ideas on how we can improve these things based on this perspective, but this is ongoing work, and we're happy to hear feedback. So just to wrap up, here the unifying principle is sort of notions of distance and similarity between data sets that help us navigate decisions in a smoother, continuous way. This could be either by the geometry induced by decisions, as in the first project, It could be through there's a distance minimization, and then the second project. And here, the main kind of decision slider is the budget. How much money, time, compute you have to spend on curating that subset that you will use. And just, our hope is that this can enable more reliable adaptation, deployment, and just more trustworthy decisions. And we're working on some follow-up projects with tabular data and synthetic data for in these decision-making settings. So overall, wrapping up the entire talk, there's a few takeaways that I want you to take from everything I said. So the first one is that the power of continuity in making choices. I argue that it's much better than having discrete choices. It opens the door to many things that we couldn't do before. And then this connection with interpolation and alignment, optimal transport makes this connection formal and interesting. Having this allows you to be much more adaptive and flexible. You don't need to settle for whatever, subset of models or data sets you were given. You can actually play with those boundaries and combine them in new novel ways. There's interesting data-centric questions to ask in the decision-making space. And just overall, interpolating is strictly better than choosing in most cases. And with that, I'm done, and I'm happy to take more questions.